let us take each of these xi's that we had before and consider the combinations we had, one at a time, two at a time, through n at a time, through 2 to the n at a time, and these were these monomials. So, the monomials, when you have k for some k, let us say, and in this case we use the letter s as a subset between 1 and n, and we have 2 to the n of those. So, x raised to the power s is the notation used to represent subset s of indices 1 through n, and we know we have 2 to the n of these indices, is simply the product using the form we just had of the xi's from that set. So, this is just a more concise notation of rewriting the form we had in the previous slide. Instead of writing long products of xi's, we can just write it as a simple term x to the power s. Okay? Now, our goal is to take this form using this more succinct representation and write it as a combination of a constant, which is a coefficient, times the value of x to the s. That is what we had before. We are simply now doing a small switch in the notation, perhaps just to be more succinct. And the main claim we want to make, which we will be justifying shortly, is you can take any Boolean function f of x and write it in this form, which is summed over all of these x raised to the s type products of the variables x1 through xn, or the variable values x1 through xn, times some constant which we will say is f hat of s. So, this is the form we are headed towards, and why are we doing this? The form that we had, where we had a basis which was driven by all possible 2 to the n inputs, might be too cumbersome, and so what we want to do is to construct an alternate basis for this vector space of all Boolean functions V that is more succinct. So, this particular form finally is the form we will start calling the Fourier expansion of the Boolean function f. F hat s is a Fourier coefficient. The collection of all the f hat s values are collectively called the Fourier coefficients of s, and together that set of the Fourier coefficients is called the Fourier spectrum of f. Just as a slight digression, the reason the word spectrum is used here is because of the roots of Fourier analysis in signal processing again, and there the particular frequencies that these signals could be decomposed into through its Fourier representation was called the spectrum, the frequency spectrum, hence that particular term spectrum. So, now we had a way of representing a Boolean function through its standard basis. The goal now is to be more clever in moving towards a basis that will allow us more efficient representations, and again we can think of this as going from one basis to another, which is a concept we have reviewed in the previous lecture, and writing any Boolean function as its Fourier spectrum form, in its Fourier spectrum form. So, given the Boolean function max2, which is our driving example, which has its multilinear polynomial which we had written earlier, half plus half x1 plus half x2 plus half x1 x2, its Fourier coefficients, if we extract them out, are half, half, half and minus half, and they are associated with the sets, the empty set in the first case, input value 1 which is x1, input value 2 which is x2, that is the index, and input value 1 2 together, which is the pair 1 2. So, now of course, if you have more inputs and say in general you have n inputs, you could have 2 to the n of these values. Looking at the general form of this set x raised to the power s, we notice that since it is a product of Boolean variables, that it itself is a Boolean function. In particular, it has the following interesting structure, that it is the exclusive OR. If you remember what good old fashioned Boolean logic tells you about different types of logic functions such as and, or, not, and of course exclusive OR, it is exactly that function that we are computing when we take the product of the xi's, and the value of that is what x raised to the power s is. It is also called the parity function. The reason is that it has the ability to detect whether the number of bits of a certain type are odd or even, hence parity. So, by a simple substitution, we have this form that is very important, which is shown as a relationship labeled number 1, which is that the function f of x, and now this is a powerful statement because it is any Boolean function, can be written as a summation this time around over all these 2 to the n subsets of indices, and what is in the sum, it is a product of some coefficient which is f hat to the power s times the value of x to the s. So, it is essentially a linear combination, by that we mean the sum where the f hat s values are constants of a range of parity functions. So, it is a very cleanly stated property, and that would be our Fourier expansion. So, if you look in the box as usual at our example, and we consider our sequence of inputs as we always did to the max 2 function, and you have a variety of possible outputs, in this case 4 possible outputs, then we also remember that this has x sub 1 sup 1 sorry, x sup 2, and in this case x sup 1 2, and as you pass these subsets through the function, you get the output representation, which is as usual the column vector, and for x sub 1 2, which is the set of indices 1 and 2, you get the output which is what we have always been looking at as a representation, I mean not the value, a column vector, which is easy to verify based on the vector shown on the slide. So, now we will use parity functions or these products of xi values to effectively encode the Boolean function. So, going back to lecture 1 and reminding ourselves what an orthonormal basis is, instead of using the standard basis that I have spoken about by way of building up intuition on how a Fourier expansion could be written down, we will now switch and move to this particular form of an orthonormal basis rooted in parity functions. So, this particular basis that we are about to introduce is also called the Fourier basis, and it is built from parity functions. So, what are some interesting properties of such a basis? So, if you start building our Fourier expansion out of parity functions, and we go back to the all important equation labeled 1 from slide number 30 and remind ourselves that form, it was the sum of some Fourier coefficients f hats times all the terms which are x raised to different subset indices, and what that means is that it is the product of the xi values from that set. That is what it was, and it is a linear combination since it is just a sum of terms which are linear. Now, the number of these parity functions in our series, the way we wrote it out in equation 1, was exponential in n, and so intuitively you would think that since we already argued that the vector space V of all Boolean functions is of dimensionality 2 to the n, we have already discussed that. What we would like to do is to point out this important but pretty simple connection. The number of parity functions being 2 to the n, and the fact that any Boolean function can be written as a sum of some coefficients times the x sup s terms, which are parity functions. It implies immediately, and that is something we can go through a fairly simple exercise to verify it for ourselves, that any time that property holds, that the sum of the form we wrote in equation 1 on slide 30 gives us the function itself, then we can deduce that that forms a basis, and also in this instance an orthonormal basis. So, what we have now is the following kind of a concluding statement which about this representation in equation 1, which is very important. So, the form that we wrote out in theorem 1, which is the form that is called the Fourier representation or the Fourier expansion of Boolean functions, that form is unique. Unique meaning it cannot be rewritten using any basis of the kind we have, which is parity functions, in any other way, and it follows from the fact that I am about to tell you, that the parity functions themselves are linearly independent, and that the number of these parity functions in that series that we wrote down as equation 1, and which is also reflected in theorem 1, equals the dimensionality. So, if there is something smaller that you could build from these parity functions, that means that the vector space V has a dimensionality less than 2 to the n, which is simply not true. So, that is the way we conclude that this representation using this particular basis parity functions is unique, and therefore, now that we know that parity functions form a basis and that any Boolean function can be represented as a linear combination of parity functions, we can actually replace Boolean functions by these vector representations, and then the same fact holds for the vectors also. What I mean by that is, instead of writing it down as these cryptic symbols that we did as x raised to some power or the product of the xi's, we could actually replace them by, since they are Boolean functions, by the vector representations of their outputs. And so, now you have a representation that is entirely based on sums of vectors multiplied by scalars, which are terms from the Fourier spectrum or the f hat terms, if you want to think of them that way. So, to close this discussion and convince ourselves that all these threads that we have developed come together nicely and tie them up, we will verify this fact using our favorite Boolean function max2. So, let us look at this example. We of course will not repeat much about max2 except to say that it has 4 parity functions as its basis, and symbolically the cryptic form is at the beginning of the slide. It is x raised to the phi, x raised to the 1, x raised to the 2, and x raised to the values 1, 2. Each parity function, as we just discussed, can be written as a vector in the space V, and without further ado, I will just claim that below each of the x phi, x1, x2, x12 values, we have simply written down what those column vectors are, which are the vector representations of those particular Boolean functions. I would say that it is not only straightforward, but perhaps even trivial to consider deduce that these are the vector representations, and the corresponding inputs that drive each element of the column vector are shown to your left. Okay? So, now we have this vector representation where max2 itself has a representation of +1, +1, +1 and -1. So, now what we want to do is, instead of thinking of the form of the Fourier expansion as being a sum of the x phi, x1, x2, x12 terms, we will now think of it as the sum of the corresponding column vectors, which are vector representations of those Boolean functions. So, what we had done at the very beginning of this lecture is we had pulled out of our hat as a magic trick the Boolean representation for max 1 max 2 for x1 x2. The Fourier expansion was half plus half x1 plus half x2 minus half x1 x2, and this you can think of in our current representation as half of x phi plus half of x1 plus half of x2 minus half of x1 x of 1 2. But what is most interesting, and this is truly conclusive, is we replace each of these x terms by their vector representations, and you can see below that once we multiply it by the scalars, which are the Fourier coefficients, what we get is exactly the vector representation of the Boolean function. So, that shows us that we have, through this exercise, derived a form which first of course went through a standard basis, then the basis as parity functions, where the parity functions are the x phi, x1, x2, x12 terms. We replace them with their column vector representations, and using the scalar terms which represent the Fourier spectrum, we are able to show that we can rewrite any Boolean function, just as we did for max 2 here, as a sum of vector representations, and that is very important, of parity functions of the form x raised to a subset of all possible indices that the variable x ranges over. So, that essentially concludes this lecture, where we now have a particular form for writing down the Fourier expansion. Of course, we have left the question open as to how we would be able to automatically derive such a form. In other words, an algorithmic approach to deriving such a form, that we promise you will be a topic for discussion in a future lecture. But for the time being, all we want to convince ourselves is somehow there is an algorithmic method for being able to derive a representation entirely based on algebraic techniques, and that is using vectors, particular column vectors, which represent parity functions. And the beautiful conclusion that we can draw is that any Boolean function can be written using a sum of these parity functions, multiplied suitably of course by coefficients which collectively represent the Fourier spectrum of that Boolean function. How we compute that, we will promise you, will be something we will discuss in the future. So, that ends this lecture. Thank you very much.